Imagine a blast so powerful it could outshine an entire galaxy, an explosion of energy so violent it ripples across the cosmos. Now picture something even stranger, a single subatomic particle hurtling through space with the force of a major league fastball, packing more energy than scientists can recreate in our most advanced machines. These are ultra-high-energy cosmic rays, and they're crashing into our atmosphere with a mystery we still can't crack. For decades, astronomers have tracked these ghostly particles, some so energetic they defy the laws of physics as we understand them. They travel billions of light-years, dodging galaxies, magnetic fields, and black holes, only to slam into Earth with energies 1,000,000 times greater than anything the Large Hadron Collider can produce. Where do they come from? What cosmic engine could possibly catapult them across the universe? Theories range from supermassive black holes to colliding galaxies, even flaws in the fabric of spacetime itself, but the truth remains as elusive as the particles themselves. Today, we're diving into the 30 most mind-bending detections of these cosmic energylantes. From the infamous, oh my god particle, a single proton moving so fast it shouldn't exist, to bizarre showers of radiation that rain down with no visible source, these events challenge everything we know about the universe. By the end of this journey, you'll see the night sky differently, knowing that somewhere out there, invisible forces are hurling particles at us with energies beyond imagination, and we're just beginning to uncover their secrets. In October 1991, scientists in Utah made a discovery so shocking they could only describe it with the words, "Oh my God." A single proton smaller than an atom had just smashed into Earth's atmosphere with the energy of a baseball traveling at 60 miles per hour. This wasn't just any cosmic ray. It carried an unprecedented 320 exa-electron volts of energy, millions of times more powerful than anything our most advanced particle colliders can produce. The oh my god particle wasn't just strong, it was impossible. According to everything we know about physics, a proton moving that fast should have slowed down long before reaching us. The universe is filled with cosmic microwave background radiation, a kind of invisible fog left over from the Big Bang. Normally, high-energy particles lose steam as they plow through this fog, like a sprinter fighting against a strong headwind. But this proton defied the rules, arriving with barely a scratch on its energy. Even more baffling was its origin. Most cosmic rays come from within our galaxy, hurled at us by supernovas or pulsars. But this particle had no business being here. It traveled billions of light-years from somewhere beyond the Milky Way, possibly launched by an unimaginably violent event in deep space. Some researchers speculate it came from a supermassive black hole, its jets acting like a cosmic railgun. Others wonder if it was spit out by colliding galaxies or even a flaw in the structure of spacetime itself. The oh my god particle forced scientists to rethink everything. If particles like this can barrel through the universe unchecked, our models of cosmic ray propagation might be missing something fundamental. Could there be undiscovered physics at play, or perhaps shortcuts in spacetime that let these particles cheat the cosmic speed limit? Whatever the answer, one thing is certain: the universe is far stranger and far more energetic than we ever imagined. The oh my god particle didn't just break records, it shattered expectations, leaving scientists scrambling for explanations. One leading theory points to dark matter, the invisible glue holding galaxies together. Some researchers speculate this mysterious substance could decay into ultra-high-energy particles, firing them across the cosmos like bullets from an unseen gun. But here's the catch: if dark matter were responsible, we'd expect to see many more particles like this, not just a rare few. The math just doesn't add up. Another mind-bending possibility involves cracks in spacetime itself. Imagine the universe as a vast cosmic fabric, normally smooth but perhaps threaded with tiny defects left over from the Big Bang. These wrinkles could act like cosmic accelerators, flinging particles to impossible speeds. The problem: we've never detected these space-time flaws directly, and current physics struggles to explain how they generate such extreme energies without leaving other traces behind. Then there's the cosmic powerhouse theory, supermassive black holes with jets of plasma stretching millions of light years. These galactic monsters could theoretically accelerate particles to near light speeds, but even their immense power falls short of explaining the oh my god particles off-the-charts energy. Somewhere in the equation, we're missing a piece of the puzzle, maybe an entirely new class of cosmic accelerators we haven't even imagined yet. The search for answers continues. New observatories like the Auger Prime upgrade in Argentina and the planned giant radio array for neutrino detection could finally crack the case by catching more of these ultra-rare particles in action. Until then, the oh my god particle stands as a humbling reminder. The universe still holds mysteries that defy our boldest theories and most advanced machines. What we learn next might rewrite the textbooks or tear them up entirely. In 2014, scientists working with the Telescope Array project in Utah stumbled upon something extraordinary: a patch of sky no bigger than your outstretched hand, radiating with an eerie concentration of ultra-high-energy cosmic rays. 19 of these extreme particles had all come from the same general direction, a small region near the constellation Ursa Major. This was no random scatter, it was a cosmic bullseye, a hotspot defying one of astronomy's oldest expectations. That ultra-high-energy cosmic rays should arrive evenly from all directions, like rain falling uniformly on a windshield. The discovery sent shockwaves through astrophysics. If these particles are born in the chaotic hearts of distant galaxies or colliding galaxy clusters, their paths should be scrambled by magnetic fields during their billion light-year journeys, scattering them randomly across the sky. Instead, this hotspot suggests something even more bizarre: a nearby cosmic particle gun firing with pinpoint precision. But here's the problem: when scientists trace the rays back to their possible origins, the closest suspect's active galactic nuclei, or AN, were still hundreds of millions of light-years away. At those distances, even the most monstrous black holes shouldn't be able to pump particles up to such insane energies without them fizzling out along the way. One leading candidate is Centaurus A, a chaotic galaxy 11 million light-years away with a supermassive black hole spewing jets of plasma into space. But while it's relatively close by cosmic standards, the math still doesn't quite fit. The particles we're detecting have so much energy, they'd need an accelerator far more powerful than anything Centaurus A's black hole seems capable of producing. Another theory points to large-scale structures, cosmic filaments or voids acting like invisible lenses, bending and focusing these particles into a narrow beam. Yet even that doesn't fully explain why we're seeing such an intense, localized concentration. The most tantalizing possibility: we might be looking at something entirely new, a previously unknown class of cosmic objects hidden in plain sight. Imagine a celestial factory humming just beyond our current telescope's reach, churning out these high-energy particles with eerie efficiency. Whatever's out there, the hotspot reminds us that the universe still holds corners where the rules don't just bend, they shatter. And with every new detection, we're one step closer to uncovering the machinery behind these cosmic anomalies. The cosmic hotspot near Ursa Major wasn't just mysterious because of its energy, it was baffling because of where it seemed to come from. When scientists traced the paths of those 19 ultra-high-energy particles backward, their trajectories pointed to something even more unexpected than a galaxy or black hole: a cosmic void. These voids are the universe's empty deserts, vast regions spanning hundreds of millions of light-years, where galaxies are few and far between. And according to everything we know, voids shouldn't be capable of producing cosmic rays at all. Think of it like finding a roaring bonfire in the middle of an empty field, with no wood, no fuel, and no explanation for how it's burning. Cosmic voids are so sparse, they lack the usual suspects: no supermassive black holes, no colliding galaxies, no supernova remnants. Yet somehow, these desolate stretches of space appear to be launching particles with energies that dwarf anything our most advanced accelerators can create. So what's really going on? One theory suggests these voids aren't as empty as they seem. Hidden filaments of dark matter might weave through them like invisible spiderwebs, and if these structures occasionally collapse or interact, they could release bursts of energy powerful enough to accelerate particles to extreme speeds. Another possibility involves rogue magnetic fields, leftover ripples from the early universe that could act like unseen slingshots, flinging particles across the void with terrifying force. Then there's the strangest idea of all. What if these cosmic rays aren't coming from the void itself, but from something behind it? Imagine a distant quasar or a galaxy cluster so far away its light hasn't reached us yet. The void might simply be a window, a clear path through the cosmic clutter, allowing particles from an even more distant and violent event to travel uninterrupted. Whatever the truth, the void alignment puzzle forces us to reconsider what's possible in the emptiest corners of the universe. If voids can somehow birth these ultra-high-energy enigmas, our understanding of cosmic accelerators might be missing a fundamental piece. And with each new particle detected from these ghostly regions, the mystery only deepens. In 2006, a high-altitude balloon floating over Antarctica detected something that made physicists question reality itself. The ANITA experiment, designed to catch whispers of cosmic rays from space, instead picked up a signal that seemed to defy the laws of nature. Unlike typical cosmic rays raining down from above, this particle appeared to burst upward through the Earth itself, as if the planet were transparent. The implications were staggering. For a particle to punch through over 5,000 miles of solid rock and ice without slowing down, it would need to be something extraordinarily rare, a tau neutrino. These ghostly particles barely interact with matter, allowing them to pass through planets like sunlight through glass. But here's the catch. The energy required for this neutrino to emerge intact would be hundreds of times higher than anything our current physics models allow. It's like throwing a baseball through a mountain and expecting it to come out the other side without a scratch. Some scientists argue the ANITA anomaly might be evidence of beyond standard model physics, perhaps a new type of particle or interaction we've never seen before. Others suggest it could hint at exotic dark matter decaying in Earth's core, producing ultra-high-energy neutrinos in the process. But skeptics counter that the signal might just be an illusion, a glitch caused by unusual ice reflections or instrumental noise mimicking a particle's path. The mystery deepened when ANITA detected not one, but several of these upward-going events over multiple flights. Each detection piled onto the controversy, with some researchers calling it the most tantalizing hint of new physics in decades, while others dismissed it as a stubborn experimental error. The debate rages on, but one thing is certain. If these detections are real, they could force us to rewrite the rules of particle physics. Until then, the Antarctic Anomaly remains one of cosmology's most delicious puzzles, a signal from the void that refuses to be ignored. The ANITA detections didn't just challenge our understanding of cosmic rays, they hinted at something far stranger lurking in the shadows of particle physics. If these upward-going particles weren't ordinary neutrinos, what could they be? One radical idea points to sterile neutrinos, a hypothetical ghost particle that could slip through matter even more effortlessly than its known cousins. Unlike regular neutrinos, which at least occasionally bump into atoms, sterile neutrinos would barely interact with anything at all, making them nearly invisible to our detectors. Yet if they exist, they might carry enough energy to explain ANITA bizarre signals without breaking the cosmic speed limit. But here's where things get even weirder. While ANITA was spotting these upward anomalies, its icy counterpart, The IceCube Neutrino Observatory buried deep in Antarctica wasn't seeing the same fireworks. IceCube, designed to catch neutrinos barreling up through the Earth, should have been drowning in similar events if sterile neutrinos were really raining down. Instead, it detected nothing out of the ordinary. This inconsistency is like two microphones picking up a thunderclap in the same room, but only one hearing the sound. Some theorists argue this mismatch might not rule out sterile neutrinos entirely. Perhaps these particles are rarer than we thought, or their interactions are so finely tuned that they only show up under specific, hard-to-catch conditions. Others suggest Anita signals could come from a different exotic source entirely like decaying dark matter particles trapped in Earth's gravity, erupting in bursts of high-energy radiation. There's even a wilder possibility. What if we're seeing the fingerprints of extra dimensions, with particles briefly tunneling through hidden layers of reality before re-emerging in our world? The debate highlights a frustrating truth in cosmic ray research. The universe loves teasing us with clues that don't quite fit. For every detector like Anita that stumbles onto something unexplainable, others like IceCube deliver silence or conflicting data. It's as if the cosmos is whispering its secrets just loud enough to make us lean in, but not loud enough to be certain. Until we catch more of these phantom particles in the act, sterile neutrinos and their ilk will remain tantalizing maybes dancing at the edges of our understanding. And that's what makes this hunt so thrilling. The next detection could be the one that changes everything. For years, astronomers assumed they knew the culprits behind ultra-high-energy cosmic rays, supermassive black holes lurking in active galactic nuclei, their monstrous jets acting like cosmic particle accelerators. But in 2018, the Pierre Auger Observatory delivered a curveball that turned this assumption on its head. After analyzing over 12 years of data tracking the most extreme cosmic rays, researchers found something startling. These ultra-high-energy particles weren't primarily linked to the usual suspects, active galaxies with their brilliant quasars and screaming jets. Instead, they traced back to a far quieter, unexpected source, starburst galaxies, where stars are born in frenzied explosions of cosmic creation. Starburst galaxies are celestial fireworks shows, cramming furious bursts of star formation into relatively small spaces. Giant molecular clouds collapse in rapid succession, birthing massive stars that burn bright and die young, all while supernova shockwaves ripple through the dust and gas. But here's the problem: these environments shouldn't be capable of producing the most extreme cosmic rays we detect. Supernovas and stellar winds are powerful, but they pale in comparison to the energy output of an active supermassive black hole. So how could these gentler galaxies be launching particles with energies that dwarf anything our largest particle colliders can muster? The mismatch throws decades of research into question. Earlier studies, like those from the High-Res Observatory, had pointed squarely at active galactic nuclei as the likely sources. Yet Auger's meticulous sky map tells a different story. One where the most violent cosmic rays seem to emerge from places that, by all rights, should be cosmic underdogs in the particle acceleration game. Some researchers argue the discrepancy might come down to distance. A starburst galaxy's relatively nearby location could make its cosmic rays easier to detect than those from more distant active nuclei. Others wonder if we're seeing a kind of celestial camouflage where the real accelerators, hidden black holes or exotic dark matter interactions, are lurking unseen within these star-forming regions. One tantalizing possibility is that starburst galaxies offer something active galactic nuclei don't: a perfect storm of turbulent magnetic fields and dense gas clouds. Imagine a cosmic pinball machine where particles ricochet endlessly off colliding shockwaves, gaining energy with each bounce until they're flung into space at unthinkable speeds. If correct, this could mean we've underestimated the power of collective stellar violence, not just single supernovas, but the combined fury of hundreds exploding in close quarters. The Auger findings don't just challenge our ideas about where cosmic rays come from, they reveal how much we still don't understand about the universe's most energetic particle accelerators. Whether starburst galaxies are truly the source or merely a signpost to something even stranger, one thing is clear: the cosmos keeps reminding us that its rules are far more flexible and far more mysterious than we've ever dared to assume. Starburst galaxies might seem like unlikely powerhouses for ultra-high-energy cosmic rays, but their chaos holds hidden mechanisms that could rewrite the rules of particle acceleration. Picture a galactic nursery where stars aren't just born. They explode into existence at a rate hundreds of times faster than in our Milky Way. Supernovas detonate like cosmic firecrackers, one after another, creating shock waves that ripple through surrounding gas clouds at millions of miles per hour. These violent waves act like natural particle accelerators, giving protons and atomic nuclei repeated kicks of energy as they bounce between collapsing stellar bubbles and expanding debris fields. Yet even this stellar frenzy shouldn't, by conventional physics, be enough to explain the extreme energies we detect. A typical supernova shockwave might boost a proton to impressive speeds, but nowhere near the jaw-dropping levels of the oh my god particle or its kin. The missing ingredient could lie in the galaxy's hidden scaffolding, vast webs of magnetic fields twisted into knots by the chaos. Imagine these fields as cosmic rubber bands, stretched taut by galactic winds, rivers of charged particles flowing outward from the starburst region. As particles surf these turbulent magnetic waves, they could gain energy in stages, much like a pinball ricocheting between bumpers at ever-increasing speeds. Recent simulations suggest this storm cellar effect might be key. When multiple supernovas erupt near each other, their combined shockwaves can create overlapping zones of acceleration, regions where particles don't just get one big push, but dozens of smaller, perfectly timed kicks. It's the difference between swinging a baseball bat once and having a machine gun of microscopic bats pummeling a particle to near light speed. Some models even hint that dense gas clouds in these galaxies could act like mirrors, reflecting particles back into the acceleration zones for extra boosts. But the puzzle isn't solved yet. Even with these mechanisms, starburst galaxies struggle to reach the theoretical energy ceiling needed for the most extreme cosmic rays. That's led researchers to propose wilder ideas, like hidden microquasars, small-scale jet-spewing black holes tucked inside star-forming regions, or dark matter particles annihilating in the galaxy's core. Others wonder if we're seeing a cosmic conspiracy where multiple galaxies along the line of sight focus and amplify rays like a gravitational lens. The starburst surprise forces us to rethink an old assumption that bigger always means more powerful in the cosmos. Sometimes it's the sheer density of violence, the packed, non-stop fury of a stellar boomtown that brews the universe's most extreme phenomena. And as telescopes peer deeper into these chaotic star factories, we might find that the universe's most efficient particle accelerators aren't the giants we expected, but the crowded, overlooked places where creation and destruction collide. The universe loves a good cosmic coincidence, but some are so precise they border on the impossible. In November 2007, the Pierre Auger Observatory in Argentina caught two ultra-high-energy cosmic rays slamming into Earth's atmosphere just hours apart. That alone wouldn't be unusual, except these particles weren't just any random pair. Both carried nearly identical energies, clocking in around 100 exa-electron volts, and both seemed to arrive from the same patch of sky. The odds of this happening by chance, roughly 1 in 10,000. This eerie doublet event wasn't just a fluke, it was a cosmic breadcrumb. When particles with such extreme energies arrive in tandem, it often hints at a single catastrophic origin. Imagine a distant explosion or collision so violent, it fired off multiple ultra-high-energy protons in the same burst, like shotgun pellets spraying into space. Yet when scientists trace the particles' paths backward, they hit a wall. No known galaxies, black holes, or other cosmic accelerators sat in that direction, just an empty stretch of intergalactic space. The mystery deepens when you consider how these twins survived their journey. Cosmic rays this powerful should interact with the cosmic microwave background, losing energy over millions of light years. For two particles to reach Earth with matching energies after such a trek, they'd need to be nearly the same age, traveling identical distances. That points to a recent, localized event, except there's nothing there. One radical explanation involves cosmic strings, hypothetical cracks in spacetime left over from the Big Bang. If these ultra-thin, ultra-dense defects exist, their snapping could release bursts of energy capable of launching paired particles across the universe. Another theory suggests a hidden magnetar, a highly magnetized neutron star flaring up just long enough to unleash these rays before fading into obscurity. The most unsettling possibility, we might be seeing echoes of an event that no longer exists. If a black hole merger or quasar collapse occurred billions of years ago, its particle burst could still be racing through the cosmos, with these two protons arriving as the last detectable remnants of a source now long gone. Whatever the truth, the 100 exa-electron-volt doublet remains a haunting clue, a cosmic whisper from the void daring us to unravel its secrets. What if the universe itself is bubbling with hidden energy, a frothy sea of quantum chaos shaping the fabric of reality? Enter quantum foam, a radical idea born from the marriage of quantum mechanics and general relativity. Theorized to exist at scales a trillion times smaller than an atom, this foamy spacetime isn't smooth and predictable like we imagine. Instead, it's a violent, seething soup where tiny black holes flicker in and out of existence, and particles might literally tunnel through microscopic wormholes. For some physicists, this isn't just wild conjecture. It could explain those eerie cosmic ray doublets. Picture those two identical ultra-high-energy particles arriving hours apart. Mainstream science points to rare active galactic nuclei flares or hidden magnetars as likely sources. But quantum foam offers a far stranger possibility. What if both particles were actually the same particle, looping back through a wrinkle in spacetime? In this mind-bending scenario, a single cosmic ray could split its path, one thread racing directly toward Earth, while another takes a detour through the foam's microscopic tunnels, emerging moments later with identical energy but a slightly delayed arrival. It's like throwing a ball through a maze of invisible portals and watching it exit twice. The math behind this idea relies on quantum fluctuations so extreme they momentarily warp the rules of causality. Normally, particles can't outpace light or teleport through barriers, but in quantum foam's chaotic dance, the very concept of distance becomes fuzzy. Particles might hop across hidden dimensions or borrow energy from the vacuum itself, cheating the universe's speed limits just long enough to create those uncanny doublets. Skeptics, of course, dismiss this as speculative fantasy. Without direct evidence of quantum foam's existence, it remains a beautiful theory with no experimental foundation. Yet the doublets and their stubborn refusal to fit conventional models keep the door cracked open. Could spacetime itself be playing tricks on us, weaving cosmic rays through secret shortcuts we can't yet see? Until we catch quantum foam in the act, the debate will rage on. But one thing's certain, if this fringe idea ever proves true, it would rewrite not just cosmic ray physics, but our entire understanding of reality itself. For now, the mystery of the doublets lingers, torn between the sober explanations of astrophysics and the dizzying possibilities of quantum wilderness. Whether born from dying stars, hidden black holes, or the universe's subatomic undercurrents, these twin particles challenge us to think bigger and smaller than ever before. And that's the thrill of the hunt. Every anomaly, every cosmic coincidence might be hiding the keys to a revolution we're only beginning to glimpse. Centaurus should be the perfect cosmic ray suspect, a chaotic, messy galaxy just 11 million light-years away, with a supermassive black hole spewing jets of plasma hundreds of thousands of light-years into space. At that distance, it's practically our neighbor, making it one of the easiest targets to study for ultra-high-energy particle production. Yet here's the paradox: when scientists crunch the numbers, Centaurus A's jets simply don't pack enough punch to explain the most extreme cosmic rays we detect. The energies don't add up like finding a child's slingshot fired a bullet with the force of a cannon. Zooming in on Centaurus A's core reveals even more confusion. Most active galaxies with powerful particle jets have tightly wound, focused beams. Think of a laser pointer versus a flickering flashlight. But Centaurus A's jets are strangely wobbly and uneven, as if something's disrupting them from within. Some astronomers suspect its black hole might be warped or misaligned, spinning at a tilt that throws off its particle acceleration efficiency. Others wonder if dense clouds of gas near the core are absorbing and scattering the jet's energy before it can launch particles to ultra-high speeds. Then there's the mystery of the dark accelerators. Could Centaurus hide pockets of extreme particle acceleration invisible to our telescopes? Imagine turbulent zones deep within the jets where magnetic fields twist into knots, creating temporary power surges that fling protons outward like cosmic pinballs. These chaotic regions might operate in bursts, brief, violent moments of acceleration too fleeting for our instruments to catch directly. Supporting this idea, some models suggest Centaurus A's jets could harbor shockwaves traveling near light speed, stacking energy onto particles like a multi-stage rocket. But the biggest question remains unanswered. If Centaurus isn't the primary source of ultra-high-energy cosmic rays, why do so many seem to point back to its general direction? One provocative theory suggests the galaxy might be a cosmic decoy, its position aligned with far more distant and powerful accelerators we can't yet see. Alternatively, its jets could be funneling particles from somewhere else entirely, acting as a celestial relay station rather than the original launcher. Centaurus A's paradox forces us to confront an uncomfortable truth. Even the closest, best-studied cosmic ray suspects can defy our expectations. Whether due to hidden dynamics, unseen physics, or sheer cosmic misdirection, this galactic neighbor keeps its secrets locked tight. And until we solve its riddles, the origin story of ultra-high-energy cosmic rays will remain frustratingly and thrillingly incomplete. Radio telescopes have peeled back another layer of Centaurus A's mystery, revealing structures that shouldn't exist. Recent observations from the Meerkat Array in South Africa uncovered faint, ghostly tendrils extending far beyond the galaxy's visible jets. These filaments don't glow in X-rays or radio waves like normal jet material. Instead, they're shadows in the cosmic spotlight, detectable only by how they warp the light of background galaxies. Scientists call them dark jets, and they might be pure rivers of kinetic energy particles moving so fast they've shed their electromagnetic signatures entirely. This discovery flips our understanding of galactic jets upside down. Normally, jets from supermassive black holes are bright beacons, visible across the universe as they slam into intergalactic gas, creating shockwaves that light up like neon signs. But Centaurus A's dark jets suggest an alternative reality, where some particle beams might travel unseen like bullets fired in perfect silence. The implications are staggering. If dark jets are real, they could explain why we've struggled to pin down the origins of ultra-high-energy cosmic rays. These invisible accelerators might be flinging particles across the cosmos right under our noses, leaving no trace except when they barrel into Earth's atmosphere. The key to this puzzle lies in what's not there. Dark jets likely consist of protons and atomic nuclei stripped of their electron shells, racing so close to light speed that they barely interact with photons. Imagine a freight train barreling through fog. If it's moving fast enough, it might not leave a ripple. These bare nuclei could carry unimaginable energy without the usual fireworks, slipping through magnetic fields that would deflect or slow ordinary particles. That might explain how Centaurus A's jets appear too weak to produce extreme cosmic rays. We've only been seeing half the picture, like judging a storm's power by its thunder while ignoring the silent lightning. But the weirdness doesn't stop there. Some theorists propose these dark jets could be threaded with exotic matter particles from the dark sector, normally invisible to us. If dark matter interacts with itself through hidden forces, it might form dense currents within the jets, acting as an unseen scaffold that boosts particles to ultra-high energies. Others wonder if we're seeing the aftermath of a black hole's failed jet, a discharge that never fully ignited, leaving behind a cascade of naked nuclei instead of glowing plasma. Centaurus A's dark jets aren't just a local oddity, they hint at a broader cosmic secret. Active galaxies across the universe might be firing similar invisible beams, their true power masked by the very efficiency of their acceleration. If that's true, our census of cosmic ray sources could be missing an entire population of shadowy particle guns. Upcoming telescopes like the Square Kilometre Array aim to hunt for more of these phantom jets, probing the gaps between what we see and what's really out there. Until then, Centaurus A stands as a reminder. Sometimes the universe's most powerful engines are the ones we can't even see. In 2019, a detector deep in Siberia sent shockwaves through astrophysics with an outrageous claim it had spotted a photon carrying 100 exa-electron volts of energy, a level so extreme it defied everything we know about light's journey through the cosmos. Photons, unlike protons or atomic nuclei, face an unforgiving gauntlet as they travel across the universe. The cosmic microwave background, the afterglow of the Big Bang, acts like a minefield for high-energy light particles, causing them to smash into other photons and decay into matter long before reaching us. For a photon to survive billions of light years at that energy would be like a snowball rolling through hell and arriving intact. The detection made by the Telescope Array's sister experiment in Russia seemed to suggest something impossible. Either our understanding of photon propagation was catastrophically wrong, or some unknown process was injecting ultra-high-energy photons directly into our cosmic neighborhood. Researchers scrambled to explain it. Could there be exotic new particles decaying into photons just outside our galaxy? Or perhaps flaws in space-time itself were bending the rules, letting these photons cheat death? The excitement was short-lived. Deeper analysis revealed a humbling truth. The signal was almost certainly a misidentified proton, a cosmic imposter mimicking a photon's signature. But the false alarm exposed a critical blind spot in cosmic ray science. Photon identification relies on the subtle details of how particles interact in detectors, showers of secondary particles, angles of impact, energy distributions. Proton showers can sometimes masquerade as photons, especially at the highest energies where detectors are pushed to their limits. The incident forced physicists to admit their tools weren't as foolproof as they'd assumed. What's fascinating is how close we came to rewriting physics based on a measurement error. The episode underscores a deeper tension in cosmic ray research, the thirst for groundbreaking discoveries versus the rigor required to prove them. It's a field where one anomaly can ignite bold theories from extra dimensions to new fundamental forces, but where false positives lurk around every corner. The phantom photon also highlighted a tantalizing what-if. If such a particle were real, it would point to cosmic accelerators beyond anything we've imagined, objects so violent they could launch light itself to energies that should be forbidden. For now, detectors have grown wiser, with upgraded algorithms better at distinguishing protons from photons. But the question lingers, could the next ultra-high-energy photon detection be the real deal? Or will it be another cosmic mirage, reminding us how little we truly understand about the universe's most energetic messengers? The cosmic microwave background isn't just leftover glow from the Big Bang. It's a minefield for high-energy photons. Imagine a bullet fired into a hallway filled with invisible tripwires. That's what happens when a photon with even a fraction of the 100 exa-electron-volt energy tries to traverse the universe. At these extreme energies, photons inevitably collide with the microwave background's lower-energy photons, triggering a process called pair production where the impact spontaneously transforms into matter, an electron and its antimatter counterpart, a positron. This isn't some rare cosmic accident, it's an unavoidable demolition derby playing out across every light year of intergalactic space. This annihilation process follows ruthless mathematical rules. For every photon above 50 exa-electron volts attempting to cross even a modest cosmic distance, the odds of survival plummet to near zero. The microwave background acts like a cosmic bouncer, ensuring no high-energy photon slips through the velvet rope of the observable universe. Yet this creates a paradox when tracing ultra-high-energy cosmic rays back to their origins. Any source capable of producing extreme photons would need to be absurdly close, within our galactic neighborhood, or possess some unknown mechanism to protect photons during their journey. Neither option fits comfortably with our current astrophysical models. Take active galactic nuclei, for example. These supermassive black hole powerhouses can theoretically generate photons at the necessary energies. But their distances, often billions of light-years away, make successful photon arrival statistically impossible. Even with optimistic assumptions about magnetic fields or photon propagation tricks, the numbers just don't add up. This forces physicists to consider alternatives like photon regeneration, where annihilated photons might somehow reconstitute themselves en route. Some speculative theories even invoke extra-dimensional shortcuts, allowing photons to bypass the microwave background's destructive influence entirely. The constraints grow even tighter when examining potential photon production mechanisms. Traditional particle acceleration in black hole jets or shockwaves creates photons alongside protons and atomic nuclei. But while the protons might survive the journey, their photon counterparts should have been obliterated long before reaching us. This mismatch suggests that either our detectors are consistently misidentifying particles, as happened with the Siberian false alarm, or that some exotic process is at work, perhaps one that generates photons much closer to home. Dark matter annihilations in our galaxy's halo present one intriguing possibility. If hypothetical heavy dark matter particles occasionally decay or collide, they could produce photon bursts locally, avoiding the cross-universe gauntlet. Another radical idea involves photons that aren't photons at all, but rather a new type of neutral particle that mimics light's behavior while being immune to pair production. Both scenarios remain speculative, highlighting how the photon survival enigma pushes us to the frontiers of known physics. This cosmic censorship of high-energy photons isn't just an academic curiosity, it acts as a crucial filter for identifying legitimate ultra-high-energy cosmic ray sources. When a candidate object like Centaurus A or a distant blazar appears to align with detected particles, the photon test becomes decisive. If the source can't plausibly deliver photons to Earth given these constraints, its candidacy weakens significantly. This realization has quietly reshaped cosmic ray astronomy, steering researchers toward sources with unexpected photon transmission properties or forcing reconsideration of how particles propagate through intergalactic space. As detectors become more sophisticated, the photon survival puzzle may hold the key to unlocking deeper truths about cosmic accelerators. Future observatories capable of distinguishing between true photons and proton imposters with near-perfect accuracy could finally settle whether any photons truly break the survival limit, and if so, what impossible engines are launching them. Until then, this enigma stands as both a frustrating barrier and an irresistible clue. reminding us that the universe's most energetic phenomena often play by rules we're only beginning to glimpse. At the heart of our own Milky Way, something strange is brewing, an excess of ultra-high-energy cosmic rays pouring from the galactic center with no obvious source to explain them. On paper, this region should be dominated by Sagittarius, a star, the supermassive black hole anchoring our galaxy. Yet despite its colossal size, 4 million times the mass of our sun, Sagittarius, a star, is oddly quiet, emitting nowhere near the energy needed to produce the cosmic rays we detect. It's like finding a bonfire raging in your backyard, but the only match nearby is a single, unlit candle. So where's the real cosmic furnace? One provocative answer might lie in the invisible scaffolding of the galaxy, dark matter. The galactic center is packed with this mysterious substance, its gravitational grip holding stars in tight orbits. Some theories suggest dark matter particles could occasionally annihilate upon collision, transforming their mass into pure energy, potentially explaining the cosmic ray excess. Imagine two ghostly particles slamming together in the void, their impact birthing a cascade of high-energy protons that rocket outward like shrapnel from an unseen explosion. But there's a catch. If dark matter were responsible, we'd expect to see a specific energy signature, a gradual drop-off in cosmic ray intensity at higher energies. Instead, the particles arriving from the galactic center cover a surprisingly broad energy range, hinting at multiple overlapping sources or an entirely different mechanism. This mismatch has led researchers to consider wilder possibilities, like the remnants of a long-dead quasar. Billions of years ago, the Milky Way's core might have hosted a blazing quasar, its black hole feasting on vast amounts of gas and spearing jets of plasma across the cosmos. Though Sagittarius, a star, is dormant now, echoes of that violent era could linger in the form of relic particle accelerators, shockwaves frozen in time or magnetic traps still hoarding ancient energy. Picture a cosmic bullet fired during the galaxy's youth, finally reaching us after eons of travel. Or perhaps the answer lies in something even more exotic. The galactic center teems with pulsars, rogue black holes, and dense star clusters, any of which could harbor unseen particle accelerators. Some models suggest colliding stellar winds in this crowded neighborhood might create turbulent zones where protons get repeatedly kicked to extreme speeds, like pinballs bouncing between flippers at hyperspeed. The enigma forces us to confront how little we understand about our own cosmic backyard. Even with telescopes trained on the galactic center around the clock, the true engine behind these ultra-high-energy particles remains hidden, a reminder that sometimes the most profound mysteries aren't in distant galaxies but right here at home. Dark matter's fingerprints might be all over the galactic center's cosmic rays, if we know where to look. Among the leading candidates are WIMP, or weakly interacting massive particles, hypothetical chunks of dark matter that could weigh anywhere from a few times the mass of a proton up to 1,000 times heavier. The beauty of WIMP lies in their dual nature, ghostly enough to evade direct detection, yet capable of annihilating when they collide, transforming their mass into bursts of energy that could seed ultra-high-energy cosmic rays. Picture two shadows colliding in a pitch-black room. Only their mutual destruction produces a flare bright enough to illuminate the walls. The math behind WIMP annihilation is tantalizing. If these particles cluster densely around the galactic center, as most dark matter models predict, their occasional collisions could produce cascades of standard model particles, including protons accelerated to staggering energies. Some simulations suggest annihilation channels favoring quark-antiquark pairs, which then decay into jets of hadrons, effectively serving as cosmic ray factories. The energy scales align eerily well. WIMP with masses in the tera-electron-volt range could theoretically produce protons with energies crossing the 100 exa-electron-volt threshold, matching the extreme particles we detect. But here's where gamma rays throw a wrench into the theory. Fermi Space Telescope observations of the same galactic center region show a gamma-ray excess that also fits WIMP annihilation models. The problem: these gamma rays appear at energies far lower than what's needed to explain the ultra-high-energy cosmic rays. It's like finding two sets of footprints at a crime scene, one from a child's sneaker, the other from a giant's boot, both allegedly made by the same suspect. This mismatch forces physicists to confront uncomfortable possibilities. Maybe WIMP aren't monolithic. Perhaps multiple dark matter particles exist, each responsible for different cosmic signatures. Alternatively, the gamma rays might come from mundane sources like pulsars, while the cosmic rays stem from something entirely separate, a cosmic case of mistaken identity. The most compelling clues come from cross-referencing cosmic ray data with gamma-ray maps. If WIMP annihilations were truly the source, we'd expect specific correlations between the two signals hotspots where both types of particles flare in sync. So far, the evidence is murky. Some regions show tantalizing overlaps, while others remain stubbornly silent. The hunt now hinges on next-generation detectors like the Cherenkov Telescope Array, which could finally resolve whether these faint whispers are the voice of dark matter or just cosmic static. Until then, WIMP remain both the prime suspect and an elusive ghost, their fingerprints smudged just enough to keep us guessing. In the vast emptiness between galaxies, an invisible war rages, one that should have wiped out the most extreme cosmic rays long before they reached Earth. This battle is governed by the Greisen-Zatsepin-Kuzmin limit, or GZK Cutoff, a fundamental rule etched into the fabric of the cosmos. Named after the three physicists who predicted it in 1966, the GZK limit declares that no particle should survive with energies beyond 60 exa-electron volts after traveling more than 150 million light-years. The reason: the cosmic microwave background, the faint afterglow of the Big Bang, acts like a minefield, sapping energy from ultra-high-energy cosmic rays as they collide with its photons. Think of it like a marathon runner trying to sprint through a hail of bullets. Even the strongest particles lose steam over cosmic distances, their energy drained by relentless collisions. For decades, this rule held firm until we started catching cosmic rays that shouldn't exist. The oh my god particle, with its 320 exa-electron volts, wasn't just an outlier, it was a direct challenge to the GZK limit. Here was a proton that had supposedly traveled billions of light-years, yet arrived with energy levels that defied the universe's strict energy tax. So how did it cheat the system? One possibility is that the particle didn't come from as far away as we think. If ultra-high-energy cosmic rays are born in our galactic neighborhood within a cosmic stone's throw of Earth, they might not have traveled far enough to suffer the GZK effect. But that raises another problem. We've yet to find any local object capable of producing such ridiculous energies. Our own Milky Way lacks the colossal black holes or violent starburst regions needed to serve as particle accelerators of this magnitude. Another explanation bends the rules of physics itself. Maybe spacetime isn't as uniform as we assume. Quantum foam, the seething, subatomic turbulence at the smallest scales, could offer microscopic shortcuts, allowing particles to bypass the worst of the microwave background's energy drain. Or perhaps magnetic fields threading through intergalactic space are more efficient at focusing and preserving these particles than our models predict, like cosmic slipstreams shielding them from the storm. The most unsettling possibility: the GZK limit might not be wrong, we might just be misunderstanding where these particles come from. If cosmic rays aren't single protons but heavier nuclei like iron or carbon, their interaction with the microwave background changes dramatically. They could retain more energy over vast distances, masquerading as rule breakers when they're really just exploiting a loophole. Whatever the truth, the GZK anomalies force us to confront an uncomfortable reality. The universe's rulebook might have pages we haven't read yet. With every ultra-high-energy cosmic ray that slips past the cutoff, we're handed another clue and another reason to question whether we truly understand the cosmos's most extreme accelerators. The answers, when they come, could rewrite not just cosmic ray physics, but our entire understanding of how energy flows through the universe. What if Einstein's relativity, the bedrock of modern physics, breaks down at energies beyond our wildest experiments? That's the daring premise behind Lorentz invariance violation, a radical idea that could rewrite the rules for ultra-high-energy cosmic rays. Named after the Lorentz transformation equations that underpin relativity, this concept suggests that at extreme energies, the fabric of spacetime might stretch or warp in ways we've never observed, subtly altering how particles move through the cosmos. If true, it could explain how particles like the oh my god particle cheat the GZK limit, arriving with energies that should have been stripped away billions of light years ago. Imagine spacetime not as a smooth, unchanging stage, but as a grainy, energy-dependent medium, like air thickening at supersonic speeds. At ordinary energies, particles obey Einstein's rules perfectly. But crank the energy up to cosmic ray extremes, and the rules might flex. Perhaps particles experience time differently at these energies, aging slower in a way that reduces their exposure to the microwave background's energy drain. Or maybe the very concept of distance shrinks for them, letting them traverse the universe in fewer steps than we'd expect. These tiny tweaks to relativity could add up to cosmic loopholes, allowing particles to punch through the GZK barrier unscathed. Testing this theory isn't just about cosmic rays, it's a cross-cosmos detective hunt. Gamma-ray bursts, the universe's most violent explosions, serve as ideal laboratories. When photons from these bursts travel billions of light years, even minuscule violations of Lorentz invariance would delay higher energy photons relative to their lower energy counterparts. It's like racing two cars where the faster one inexplicably hits invisible speed bumps. Experiments like the Fermi Gamma-Ray Space Telescope have scoured burst data for these delays, and while most observations align with standard relativity, a handful of anomalies keep the door cracked open. Neutrinos offer another tantalizing test case. These ghostly particles detected by observatories like IceCube should arrive in tight synchrony with gamma rays if relativity holds. But if Lorentz invariance falters at ultra-high energies, high-energy neutrinos might show up early or late like guests arriving at a party before the invitations were even sent. So far, no definitive timing quirks have emerged, but the search grows more precise with every new neutrino detection, the most mind-bending implication. If Lorentz invariance violation is real, it might hint at quantum gravity, a theory unifying relativity with quantum mechanics. Just as quantum particles blur the lines between waves and particles, space-time itself could become fuzzy at extreme scales, its usual rules flickering in and out of existence. For now, these ideas remain at the frontier of physics, where every unexplained cosmic ray is a potential clue, and every detection a chance to glimpse the universe's hidden rulebook. One thing's certain, if relativity isn't absolute, the cosmos just got a whole lot stranger. In 2020, scientists tracking ultra-high-energy cosmic rays faced a detection so perplexing it seemed to come from nothing at all. A particle with over 100 exa-electron volts of energy slammed into Earth's atmosphere, but when researchers traced its path backward, they found no galaxies, no black holes, not even a stray star cluster in its origin direction. Just an endless cosmic desert stretching for at least 100 million light-years in every direction. This wasn't just a mystery. It was a direct affront to everything we thought we knew about how particles reach such extreme speeds. The so-called empty sky event appends the most basic rule of cosmic ray origins, that extreme energies require extreme environments, active galactic nuclei, colliding galaxies, even magnetars. All the usual suspects depend on colossal gravitational or magnetic forces to whip particles to near light speeds. But this particle arrived from a region so devoid of matter, it's like a cannonball fired from an abandoned battlefield with no cannon in sight. If voids truly can accelerate particles to these energies, we might be missing an entire chapter in astrophysics, one where emptiness itself holds hidden power. One unsettling possibility involves the large-scale structure of the universe. Between galaxy clusters stretch vast filaments of dark matter, invisible threads weaving the cosmic web. Though these filaments contain little ordinary matter, their gravitational pull might create shock waves as they interact, generating turbulent magnetic fields capable of particle acceleration. Picture a silent, invisible river, one whose currents are strong enough to fling debris at unimaginable speeds, even though the riverbed itself is empty. A wilder theory suggests these cosmic rays might not originate in the void at all, but somehow punch through it from somewhere even more distant. If space-time curvature or quantum effects focus particles like a lens, the void could simply be a clear channel, a cosmic hallway guiding particles from an unseen accelerator far beyond our observational horizon. Alternatively, the particles could be relics from a primordial universe created in the first seconds after the Big Bang and only now reaching us after eons of travel. The implications are staggering. If voids can produce ultra-high-energy cosmic rays, we might need to rethink the very nature of cosmic acceleration. Magnetic fields threading through nothingness, dark matter interactions we can't yet detect, or even flaws in spacetime itself could be lurking in these empty regions, quietly orchestrating particle energies that dwarf anything our most advanced colliders can muster. Upcoming observatories like the POMA mission aim to scan these voids for faint electromagnetic whispers that might betray hidden mechanisms. Until then, the empty sky event stands as a haunting reminder. Sometimes the universe's greatest mysteries aren't in the brightest places, but in the darkest, emptiest corners we've overlooked. The cosmic web isn't just a backdrop of the universe, it's a dynamic, thrumming network where galaxies are strung along invisible filaments like pearls on a string. These filaments, made mostly of dark matter and diffuse gas, stretch for hundreds of millions of light years, weaving the largest structures in existence. When these colossal threads collide, they don't just pass through each other quietly. The impact sends shockwaves rippling through the intergalactic medium, a tsunami of energy capable, in theory, of accelerating particles to extreme speeds. It's like dropping a boulder into a still pond. Only the ripples here are powerful enough to fling protons across the cosmos. But here's where reality clashes with possibility. While simulations show these shockwaves can accelerate particles, the energies they produce barely scratch the surface of what we see in ultra-high-energy cosmic rays. The most optimistic models top out around 10 exaelectron volts, a fraction of the oh my god particle's jaw dropping 320. The problem lies in the chaotic nature of these collisions. Unlike the focused jets of a black hole or the dense fury of a starburst galaxy, shockwaves in the cosmic web are messy and diffuse. Particles get buffeted in all directions, losing energy as often as they gain it, like a pinball bouncing between flippers with no clear path to the high-score lane. Another hurdle is time. Cosmic web shocks unfold over hundreds of millions of years, a slow-motion car crash by astrophysical standards. For particles to reach ultra-high energies, they'd need to surf these shockwaves continuously, gaining incremental boosts without getting thrown off course. But the universe doesn't offer such perfect conditions. Turbulence, magnetic field irregularities, and the sheer vastness of these filaments all conspire to cap the maximum energy achievable. Even under ideal scenarios, the numbers just don't add up. Yet the cosmic web isn't completely off the hook. Some theorists speculate we might be missing a crucial piece of physics, perhaps hidden magnetic amplifiers lurking in the filaments, or pockets of extreme turbulence that act like cosmic boost pads. Others wonder if multiple shockwaves could stack their effects, creating a Chinese letter race where particles get passed from one wave to the next, each adding a little more energy. It's a tantalizing idea, but one that requires conditions so precise they'd be rarer than a winning lottery ticket in the void. Until simulations can bridge this energy gap, the cosmic web remains a fascinating but flawed suspect in the ultra-high-energy cosmic ray mystery. Its vast scales and titanic collisions make it a compelling candidate on paper, but the universe seems to demand something even more extreme to explain the particles raining down on Earth. Whether the answer lies in undiscovered physics or entirely new cosmic accelerators, one thing is clear. The cosmic web's whispers of acceleration are loud, but not quite loud enough, at least not yet. Iron nuclei shouldn't survive a cosmic journey, at least not according to the rules of physics. These heavyweight atomic fragments, packed with protons and neutrons, are notoriously fragile when hurtling through space. Slam them into a stray photon or gas particle at near light speed, and they'll shatter like glass, breaking into smaller, lighter pieces long before reaching Earth. Yet detectors have caught ultra-high-energy iron nuclei arriving intact, their dense cores unscathed after traveling millions, possibly billions of light years. It's like finding a delicate china teacup that somehow survived being thrown across a battlefield. This anomaly points to something profoundly strange about their origins. Typical cosmic ray factories, active galactic nuclei, gamma-ray bursts, even colliding galaxy clusters, are rich in hydrogen and helium, the universe's lightest and most abundant elements. Heavy elements like iron are forged in supernova explosions or neutron star mergers, violent but localized events that usually don't produce the sustained acceleration needed for ultra-high energies. So where are these iron freight trains coming from? One clue lies in their energy profile. Unlike lone protons, which can be whipped to extreme speeds by even modest accelerators, iron nuclei require far more power to reach the same velocities. Their detection suggests a source not just energetic, but specifically tuned to catapult heavy elements, a cosmic cannon designed for cannonballs, not bullets. Some theorists point to rare, iron-rich supernovas in dense stellar nurseries, where shock waves from successive explosions might act like a multi-stage booster rocket for nuclei. Others speculate about tidal disruption events, where stars ripped apart by black holes could spew out streams of heavy elements ripe for acceleration. The most unsettling possibility, these iron nuclei might not have traveled far at all. Their survival could hint at hidden accelerators lurking uncomfortably close to Earth, perhaps within our own galaxy or its nearby satellites. Imagine a previously overlooked neutron star binary or a rogue black hole drifting through the Milky Way's halo, its gravitational fury ejecting heavy nuclei like cosmic shrapnel. Supporting this idea, some iron-rich cosmic rays appear clustered in certain sky regions, as if tracing back to a local powerhouse we've yet to identify. The implications ripple beyond astrophysics. If iron nuclei can endure interstellar and intergalactic trips at these energies, our models of particle propagation need serious revision. Maybe magnetic fields in galactic halos are far stronger than we thought, shielding heavy nuclei like an invisible force field. Or perhaps iron's complex structure lets it cheat disintegration through quantum effects we don't yet understand. Every detection chips away at the boundaries of known physics, revealing a universe more innovative and more mysterious than we ever guessed. What's clear is this: the iron nuclei surprise isn't just a curiosity. It's a signpost pointing to cosmic engines unlike anything in our current catalogs, places where the universe's heaviest elements are forged, flung, and preserved against all odds. And with each new heavy nucleus spotted, we're one step closer to uncovering these hidden crucibles of the cosmos. Neutron star mergers aren't just cosmic light shows, they might be nature's ultimate particle accelerators. When these ultra-dense stellar corpses spiral together and collide, They don't just create gravitational waves and bursts of gold. The relativistic jets they spew could be the missing link to those puzzling iron-rich ultra-high-energy cosmic rays. Picture two city-sized objects, each more massive than our Sun, smashing together at a third the speed of light. The shock waves from such an impact don't just glow, they blast out material faster than most cosmic objects can dream of, with magnetic fields trillions of times stronger than Earth. The numbers tell a compelling story. A single neutron star merger can eject over 1% of its mass at near light speeds. That's roughly 10 Jupiters worth of material suddenly racing through space. Within this expanding fireball, iron and other heavy elements get caught in swirling electromagnetic maelstroms, gaining energy with each pass like marbles in a cosmic pinball machine. Simulations show these conditions could theoretically accelerate iron nuclei up to several hundred exaelectron volts, crossing the threshold of the most extreme cosmic rays we detect. But there's a hitch: distance. Most neutron star mergers occur so far away that even their fastest ejector should lose energy over intergalactic distances due to interactions with the cosmic microwave background. That's where kilonovae, the brilliant aftermath of these collisions, offer a game-changing twist. The R-process nucleosynthesis happening in these explosions doesn't just make gold and platinum, it creates vast quantities of unstable, neutron-rich isotopes. As these isotopes decay, they pump extra energy into nearby iron nuclei like microscopic afterburners, potentially giving them enough of a boost to survive the journey to Earth. The smoking gun might lie in timing. When LIGO detected its first neutron star merger in 2017, gamma-ray observatories noticed something curious: a faint, lingering afterglow of high-energy radiation lasting weeks longer than expected. Some theorists now suggest this could be the signature of iron nuclei being continuously re-accelerated by the decay of freshly forged radioactive elements, a process that might explain how heavy cosmic rays maintain their energy over cosmological distances. Yet mysteries remain. Current models struggle to explain why we don't see more iron-rich cosmic rays if mergers are truly prolific producers. One possibility is that only certain types of collisions, perhaps those involving highly magnetized neutron stars or unusually asymmetric pairs, can generate the perfect storm of conditions needed to launch intact iron nuclei across the universe. Another wrinkle comes from recent observations showing that mergers might produce more lightweight elements than previously thought, potentially diluting the iron output. The hunt for answers is driving new generations of detectors. Upcoming gravitational wave observatories like the Einstein Telescope will pinpoint mergers with unprecedented precision, while cosmic ray arrays search for telltale patterns in arriving heavy nuclei. If a future neutron star collision coincides with a surge of ultra-high-energy iron particles, we might finally have our cosmic Rosetta Stone, proof that the universe's most violent weddings are also its most powerful particle guns. Until then, these stellar smash-ups remain both prime suspects and tantalizing enigmas in our quest to understand nature's ultimate energy extremes. In July 2012, detectors across the globe picked up something bizarre: a rapid-fire barrage of cosmic rays, all striking Earth's atmosphere within a single frantic 10-minute window. These weren't the usual ultra-high-energy outliers, but a coordinated volley of mid-energy particles, each packing enough punch to light up multiple sensors at once. The timing was too precise to be coincidence, the clustering too tight for random chance. Whatever fired this cosmic salvo wasn't just powerful, it was blisteringly fast, a celestial trigger pulled and released in less time than it takes to brew a cup of coffee. Theories erupted like the particles themselves. Could this have been a magnetar, a highly magnetic neutron star experiencing a catastrophic starquake? These dense stellar remnants occasionally unleash flares so intense they briefly outshine entire galaxies. When magnetar surfaces crack under immense magnetic strain, the resulting energy release can hurl charged particles across space like shrapnel from an exploding cannon. But here's the catch: magnetar flares typically last mere milliseconds, not minutes. For one to sustain particle acceleration for 10 straight minutes would require energy reserves beyond anything we've observed, like a firework burning at full intensity for an hour instead of vanishing in a flash. Another contender emerged from an unlikely corner of astrophysics: fast radio bursts, or FRB. These mysterious, milliseconds-long blasts of radio waves have puzzled scientists for years, with some linked to magnetars, others to entirely unknown phenomena. While FRBs themselves don't produce cosmic rays, their explosive origins might. Imagine a magnetar's flare or a collapsing black hole's death throes generating both an FRB and a secondary particle burst, one racing ahead as radio waves, the other trailing as cosmic rays. The timing mismatch could stem from propagation delays, with particles taking slightly longer to traverse interstellar magnetic fields than their photon counterparts. Yet no FRB was detected alongside this 10-minute cosmic ray burst, leaving the connection tantalizing but unproven, the most intriguing possibility. A fleeting cosmic particle cannon, something too brief to appear in telescope surveys, too violent to be ignored. Picture a wandering black hole shredding a passing star, its tidal forces stretching the doomed object like taffy before igniting a particle jet in a singular, unsustainable burst. Or consider a pair of neutron stars merging in a distant galaxy, their collision birthing a short-lived accelerator that flickers out almost as quickly as it forms. These transients are the universe's one-hit wonders, events so rare and fast we're lucky to catch even their echoes. What makes this 10-minute burst uniquely frustrating is its middle ground energy. Ultra-high-energy cosmic rays point clearly to extreme accelerators. Low-energy ones blend into the background noise, but this event sits in the awkward in-between, energetic enough to demand explanation, yet not extreme enough to narrow the suspects. It's like hearing a gunshot from an unknown firearm, too loud to dismiss, too generic to identify. As detectors grow more sensitive, the hope is to catch another of these fleeting bursts in the act, preferably with a neutrino or gamma-ray counterpart to triangulate the source. Until then, the 10-minute enigma remains a cosmic riddle, a reminder that the universe doesn't just operate in slow-motion grandeur, but in split-second violence we're only beginning to witness. Time itself might hold the key to unlocking the mystery of that frantic 10-minute cosmic ray burst. When objects move at nearly the speed of light, or exist in extreme gravitational fields like those around neutron stars, the fabric of time warps dramatically. A single second for the collapsing star could stretch into minutes from our perspective, like watching a high-speed video played in slow motion. This relativistic time dilation could transform what was originally a split-second explosion into the prolonged particle barrage we detected. Imagine a neutron star on the brink of collapse. As its core implodes under its own gravity, the star's outer layers rebound violently, ejecting material in a shockwave traveling at nearly light speed. For an observer riding that shockwave, the event might last mere milliseconds, but for us, watching from billions of miles away, the extreme velocities would stretch that emission into minutes, every particle's trajectory elongated by the sheer physics of relativity. It's like shining a flashlight while sprinting at near light speeds. The beam's photons would appear to crawl from an outsider's view, even as they raced forward from your own. This effect could explain why the burst lasted so much longer than typical magnetar flares or fast radio bursts. The particles weren't being emitted gradually, they were fired all at once, but relativity smeared their arrival across 10 minutes like cosmic taffy. Supporting this idea, some models of collapsing neutron stars predict precisely this kind of time-stretched emission, where ultra-relativistic ejecta create apparent slow-motion bursts when viewed from Earth. The energy profiles match two mid-range cosmic rays could easily be byproducts of a collapsing star's shockwave, ferociously accelerated but not quite reaching the extremes of black hole jets. Yet there's a snag: time dilation alone can't account for the burst's precise clustering. If the particles were simply stretched by relativity, we'd expect a smoother distribution, not the tight, rapid-fire sequence observed. This suggests something more complex, perhaps multiple shock layers in the collapsing star fired particles in quick succession, each wave's emission stretched just enough to overlap with the next. Picture a machine gun firing bullets at relativistic speeds. Each shot sound arrives slower, blending into the next until the whole burst sounds like one sustained note. The implications ripple far beyond this one event. If relativistic time dilation can sculpt cosmic ray bursts into such deceptive profiles, we might need to re-examine other transient phenomena. Mysterious gamma-ray flashes, puzzling neutrino cascades. Could some of these also be stretched or compressed by the universe's warped sense of time? The next generation of multi-messenger observatories might catch a neutron star's collapse in gravitational waves, neutrinos, and cosmic rays simultaneously, letting us see the same event through different relativistic lenses. Until then, this 10-minute enigma stands as a tantalizing hint that in the cosmos, even time itself can be a trickster. Scientists call it the cosmic ray that shouldn't be, a particle so powerful it left detectors buzzing with disbelief. When researchers traced its path backward through the galaxy, the results defied every expectation. According to our best maps of the Milky Way's magnetic fields, this ultra-high-energy cosmic ray should have bent left. Instead, it curved right, as if the universe itself had flipped the script. The implications are staggering. Either our understanding of galactic magnetism is profoundly flawed, or we're glimpsing entirely new physics at play. Galactic magnetic fields are like invisible rivers winding through space, gently steering charged particles along meandering paths. For decades, astronomers have relied on these maps to backtrack cosmic rays to their origins, trusting that a particle's arrival direction, adjusted for magnetic deflection, would point roughly to its birthplace. But this rogue particle shattered that assumption. It appeared to hail from a nearby star-forming region in the Milky Way, yet its trajectory ignored the magnetic currents that should have guided it there. Imagine tossing a paper airplane into a steady breeze only to watch it soar backward against the wind. One explanation cuts deep: our field maps might be missing something critical. The Milky Way's magnetism isn't uniform. It's a tangled web of local swirls and eddies, shaped by supernova bubbles, stellar winds, and gas clouds. Current models approximate these fields using sparse measurements, leaving gaps the size of solar systems. If this cosmic ray slipped through an uncharted pocket of reversed magnetism, its path might not be so impossible after all. Recent simulations suggest these magnetic knots could be far more common than we thought, hidden in the turbulent wakes of dying stars or the voids between spiral arms. But there's a wilder possibility that the particle's defiance hints at undiscovered forces. Quantum entanglement, extra dimensions, even fleeting dark matter interactions could subtly alter a particle's trajectory in ways standard physics can't yet explain. Some theorists speculate that ultra-high-energy cosmic rays might briefly feel exotic fields invisible to ordinary matter, like a ship's compass mysteriously tugged by an undersea current. Others wonder if space-time itself behaves differently at these energies, warping particle paths in unpredictable ways. The stakes couldn't be higher. If galactic magnetism is more complex than our maps suggest, it undermines decades of cosmic ray research, forcing us to redraw the Milky Way's hidden infrastructure. But if new physics is at work, we're staring at a revolution, one where particles obey rules we've yet to write. Upcoming missions like the Square Kilometre Array aim to map galactic fields with unprecedented precision, while next-gen cosmic ray detectors hunt for more of these rebellious particles. Until then, this backwards cosmic ray remains a cosmic riddle, a single particle that could rewrite either our maps or our textbooks. deep in the fabric of the cosmos, hidden threads might be weaving an invisible web, one that's been stretching and twisting since the dawn of time itself. These are primordial magnetic fields, relics from the universe's infancy, potentially forged in the first trillionth of a second after the Big Bang. Unlike the magnetic fields we know, those tied to stars, galaxies, or even galaxy clusters, these ancient forces could span the entire universe, subtle yet pervasive, like ghostly currents running through the walls of reality. And if they exist, they might hold the key to why some ultra-high-energy cosmic rays arrive at Earth on paths that defy all expectations. Picture the early universe not as a smooth, featureless soup, but as a seething cauldron of quantum fluctuations. In that chaos, slight imbalances in the newborn cosmos could have generated weak magnetic fields, imprinting them onto the fabric of space-time as the universe expanded. Over billions of years, these fields would have stretched to unimaginable scales, forming a diffuse network of magnetic tendrils threading through the voids between galaxies. They'd be faint, far weaker than the fields near a pulsar or black hole, but their sheer size could make them cosmic puppeteers, gently tugging charged particles like cosmic rays onto unexpected trajectories. This might explain the bizarre deflections we've observed. A proton hurtling across the universe would normally be steered by the Milky Way's magnetic fields, its path curving like a paper airplane in a breeze. But if primordial fields are layered atop these local forces, they could twist particles in ways our current models don't account for. Imagine a river whose surface currents flow east while hidden deep below, an older, slower current pulls west. A cosmic ray might end up somewhere entirely unpredictable, its origin obscured by this dual influence. The implications ripple far beyond cosmic rays. If these fields are real, they could rewrite our understanding of cosmic evolution. Some theories suggest they might have shaped the first galaxies, their subtle pressures guiding where gas collapsed into stars. Others speculate they could even leave faint imprints on the cosmic microwave background, subtle swirls in the afterglow of the Big Bang that we've yet to detect. The search is already underway, with radio telescopes scanning the skies for telltale distortions in the light from distant quasars, hunting for the fingerprints of magnetism older than stars themselves. Yet proving their existence is a staggering challenge. Unlike the magnetic fields around a neutron star, which scream their presence with pulses of X-rays and radio waves, primordial fields would whisper. Detecting them would require catching the faintest of imprints, perhaps a slight polarization in the light from the universe's first atoms, or a statistical oddity in the paths of thousands of cosmic rays. It's like trying to hear a single note of a symphony played at the edge of the universe, with all of space and time as static in between. For now, primordial magnetic fields remain a tantalizing what-if. But with every cosmic ray that arrives askew, with every anomaly in our magnetic maps, the case for their existence grows just a little stronger. If confirmed, they'd open a window to the universe's first moments, a time when the laws of physics as we know them were still writing themselves. And in that window, we might finally find the missing piece to the puzzle of why the cosmos' most energetic particles keep defying the rules. Some cosmic accelerators might be cheating the universe's own timekeeping rules. Take Blazar PSO J0309+27, a monstrous black hole 4 billion times more massive than our Sun, spearing the cosmos with twin jets of plasma traveling near light speed. When researchers traced an ultra-high-energy cosmic ray back to this distant powerhouse, they hit a paradox. The Blazar appeared far too young to have produced such an energetic particle. Its light suggested an age of merely 100 million years, barely enough time for its jets to rev up to full strength, let alone launch particles with energies surpassing 100 exa-electron volts. The conflict lies in how black hole jets mature. Like cosmic engines, they don't reach maximum power instantly. As a supermassive black hole feeds, its magnetic field coils tighter, spinning faster and focusing its jets into ever more potent particle beams. Early in a blazar's life, its jets should sputter and wobble like a fledgling rocket struggling to stabilize. Yet this cosmic ray arrived with the precision of a particle fired from a well-oiled machine, one that theoretically shouldn't have existed when the blazar was still in its cosmic infancy. One explanation plays with the concept of light speed delays. The blazar's visible light took nearly 12 billion years to reach us, but its cosmic rays, being slowed slightly by interactions with intergalactic magnetic fields, might have dawdled along the way. If the particle was launched later in the blazar's life, but arrived only slightly after its youthful light, the timing could appear artificially compressed from our perspective. Think of it like hearing a cannon's roar moments after seeing its flash, except stretched across billions of years. Simulations suggest this delay could age the blazar just enough to resolve the discrepancy if its jets matured unusually fast. But not all scientists buy this fix. Alternative theories propose that some blazars might skip the awkward teenage phase entirely, their jets achieving extreme energies through mechanisms we've yet to understand. Imagine a black hole born with its magnetic fields already perfectly aligned, its accretion disk so dense and turbulent that particle acceleration kicks into overdrive immediately. Others speculate these young blazars might tap into hidden energy sources, dark matter annihilations in their cores, or quantum effects in their ergospheres, giving their jets an unnatural head start. The debate forces us to confront how little we truly know about black hole adolescence. Upcoming telescopes like the Cherenkov Telescope Array aim to catch more of these cosmic overachievers in the act, hunting for telltale flares that betray their true ages. Until then, PSO J0309+27 stands as both a cosmic conundrum and a tantalizing clue that the universe's most powerful engines might have surprises lurking in their early years. A wobbling jet might be the universe's best magic trick, hiding its true age behind the illusion of youth. Blazars like PSO J0309+27 fire particle beams so narrow and precise, they act like cosmic lighthouse beams slicing through the darkness. But what if those beams aren't as steady as they appear? Jet precession, the slow gravitational wobble of a black hole's spin axis, could make even an ancient accelerator masquerade as a newborn. Picture a spinning top slowly tracing circles as it loses speed, its tip carving invisible loops in the air. Now imagine that top is a supermassive black hole, and its swirling motion tilts the entire jet like a garden hose writhing under pressure. This subtle dance could solve the blazar age paradox. When we observe a distant jet, we're only seeing it at one frozen moment in its precession cycle, like catching a single frame of a spinning dancer mid-twirl. If the jet's current orientation points almost directly at Earth, we see it as a brilliantly luminous blazar. But rewind the cosmic clock, and that same jet might have been aimed elsewhere, its earlier particle acceleration phases invisible to our telescopes. The black hole could have been flinging ultra-high-energy cosmic rays for eons before its wobble brought the beam into our line of sight, making it appear artificially young. The math behind this sleight of hand is startlingly elegant. Some models suggest precession cycles lasting millions to billions of years, with jets tracing slow, majestic arcs across the sky. A black hole's spin might get tugged by misaligned accretion disks or the gravitational pull of a binary companion, introducing a gentle sway that compounds over millennia. For PSO J0309+27, this could mean its particle cannon was already operating at full tilt long before its light reached us. Its earlier cosmic rays just didn't head our way until the jet's precession hit the right angle. There's tantalizing evidence this isn't just theoretical. Some blazars show periodic brightness variations in their gamma-ray emissions, flickering like a candle in a slow breeze. These oscillations match predictions from precession models, where the jet's changing orientation alters how much radiation spills toward Earth. Even more compelling are the rare blazars caught mid-wobble, their jets visibly curving in radio telescope images like the tail of a celestial whip. These bent beams suggest precession isn't just possible, it's actively shaping how we perceive cosmic accelerators across the universe. Yet precession alone can't explain everything. The most extreme cosmic rays demand such staggering energies, even a perfectly aligned jet might struggle to produce them early in a blazar's life. That's where turbulence in the accretion disk comes in. Simulations show that young, chaotic disks can channel energy into jets with freakish efficiency, like a storm funneling wind into a rogue wave. Combined with precession, this could let fledgling blazars punch above their weight class, their particle beams amplified by the very instability that makes them wobble. The implications rewrite how we trace cosmic rays back to their origins. If jets precess, their apparent positions on the sky could be cosmic mirages, like following a flashlight's beam to find it's being swung by a runner you can't see. Future observatories might need to account for this motion, reconstructing the full arc of a jet's history to pinpoint where and when a cosmic ray truly began its journey. Until then, the wobble of distant black holes remains both a solution and a warning. In the cosmos, even the straightest lines can be curves in disguise. What if the next ultra-high-energy cosmic ray to hit Earth doesn't just break records, it shatters physics itself? Imagine a particle screaming through space at 1,000 exaelectron volts, carrying the kinetic energy of a freight train in a single subatomic package. This isn't just a theoretical extreme, it's a potential reality lurking in our cosmic future, one that would force us to tear up the rulebook on how the universe accelerates matter. Current models of cosmic accelerators, black holes, starburst galaxies, colliding neutron stars all hit a hard ceiling around 500 exaelectron volts. Push beyond that, and you enter a realm where known physics simply can't explain how particles reach such energies without disintegrating into cascades of lower energy fragments long before reaching Earth. A 1,000 exaelectron volt detection wouldn't just be unusual, it'd be an existential crisis for astrophysics, screaming that we're missing something fundamental about the fabric of spacetime itself. That's where projects like the Giant Radio Array for Neutrino Detection, or GRAND, come in. This ambitious observatory, planned for remote deserts and mountain ranges across 3 continents, won't just hunt for cosmic rays, it'll be a tripwire for the impossible. Unlike traditional detectors that wait for particles to strike Earth's atmosphere, GRAND tens of thousands of antennae will listen for the radio whispers of ultra-high-energy neutrinos and cosmic rays as they interact with our planet's magnetic field. The goal: catch the uncatchable particles so energetic they'd make the oh my god particle look tame. The technical hurdles are staggering. At these energies, cosmic rays become vanishingly rare, perhaps 1 per century per square kilometer of Earth's surface. GRAND's strategy is brute force coverage, an array spanning 200,000 square kilometers, an area larger than Nebraska, to stand any chance of snagging these cosmic white whales. Even then, distinguishing a genuine 1,000 exaelectron volt event from background noise will require algorithms trained to spot patterns finer than a fingerprint in a sandstorm. But the payoff could rewrite science. Such a detection might reveal primordial defects in spacetime cosmic strings left over from the Big Bang, snapping like overstretched rubber bands to release bursts of energy that dwarf quasars. Or it could expose hidden dimensions, with particles tunneling through unseen layers of reality to cheat the universe's energy limits. Some theorists even speculate about dark accelerators, objects made entirely of dark matter whose collisions spit out ordinary particles at energies we've never witnessed. The clock is ticking. Current observatories like the Pierre Auger Array have already pushed detection thresholds to their limits, leaving a tantalizing gap where these monster particles might lurk. If GRAND or its successors spot even a single 1,000 exa-electron-volt cosmic ray, the implications will ripple far beyond astrophysics, touching everything from quantum gravity to the nature of dark matter. Until then, we're left with a thrilling uncertainty. The next particle to strike Earth could be the one that changes everything, or the one that never comes at all. From the oh my god particle's impossible energy to the eerie void-born rays that materialize from nothing, these 30 cosmic anomalies aren't just curiosities, they're cracks in the foundation of modern physics. Each one defies explanation in its own way, whether it's iron nuclei surviving impossible journeys, particles arriving from galaxies too young to host them, or cosmic rays tracing back to empty voids where nothing should exist. Collectively, they paint a picture of a universe far stranger and more dynamic than our textbooks describe, one where black holes might wobble like spinning tops, dark matter could decay into invisible particle jets, and space-time itself might be threaded with hidden flaws left over from creation. What makes these mysteries so electrifying isn't just their defiance of the rules, it's what they reveal about how much we still don't know. The oh my god particle alone forced us to reconsider how particles traverse billions of light years without losing steam. The Anita anomalies teased the existence of sterile neutrinos or even extra dimensions, and the galactic center's unexplained cosmic rays hint that dark matter might be colliding right in our cosmic backyard. Every detection is a clue, a breadcrumb leading toward revelations that could rewrite entire branches of science. This isn't just about astrophysics. Crack one of these enigmas, and the ripple effect could transform everything from quantum computing to energy production. Imagine harnessing the power of a blazar's jet, or decoding the acceleration mechanisms behind neutron star mergers. Even the failures like the Siberian phantom photon teach us humility, reminding us that nature's playbook is deeper than our theories can reach. So here's the real question: which cosmic ray keeps you up at night? Is it the eerie precision of the 10-minute burst, the backwards traveling particle that ignored galactic magnetism, or the starburst galaxies quietly outshining black holes? Drop your pick in the comments and don't forget to subscribe. Because in the hunt for answers, every observation, every theory, and every wait that shouldn't be possible moment brings us one step closer to the next great breakthrough. The universe is talking. All we have to do is listen.